So what I want to talk about today is adding and subtracting radical expressions. In a lot of cases, this is a lot like adding, or in a lot of respects, this is a lot like adding polynomials in that we basically want to add like terms. And the challenge here is to get our individual terms simplified to a form where they readily add. So instead of like terms, what we have in a polynomial, we're going to have like radicals. And so what we mean by this is that the index of the, it has the same index and the same radicand. So what I mean by this is that all of these on this first line, 2 root 2, 3 root 2, just the square root of 2, negative 7 root 2, these are like radicals, okay, because they all have the square root of 2 in them. Same index, same radicand. Another example with cube roots, the cube root of 3, 2 times the cube root of 3, and negative 10 times the cube root of 3 are all like radicals as well. And so we can add like radicals and simplify expressions that way. So for adding and subtracting, it works a lot like polynomials in the sense that we keep the radical the same, and then we add the coefficients to the radical. And so square root of 2 plus 3 times the square root of 2 is 4 times the square root of 2. If we have the square root of 3 plus 4 times the square root of 2 plus 7 times the square root of 3 minus the square root of 2, notice there's two different kinds of radicals in here, the square root of 2 and the square root of 3. So the only ones you can add are the ones that have the same radical. So in this case, we can add the square root of 3's together, and so we have 8 root 3, and then we can do the 4 square root of 2 minus the square root of 2 and get 3 square root of 2. So the trick to doing these things is to simplify whenever we're adding. So if we have something like the square root of 20 plus the square root of 45, at face value it doesn't look like that can get any simpler. But if you first simplify the radicals, so you factor 20 into 2 squared times 5, and you factor 45 into 3 squared times 5, these simplify into 2 root 5 plus 3 root 5, and of course you can add then the 2 and the 3 to get 5, and so we have 5 root 5. So you always have to simplify first and then see what adds. It could be that you simplify them and nothing can happen because you get different radicals. Then you're as simple as you can get. But if you do have like radicals, then you should add them. All right. So here's a few examples. So if I have 4 radicals that all involve a radical 2, I can just take 2 plus 5 minus 1 plus 3, and so I get 9 square root of 2. Now this also works when you have variables in there. The variable can be either outside of the radical or inside of the radical, and you just follow the same rules. So here we have a 7 times the square root of x plus 2 square root of 2 minus 3 square root of x plus square root of 2. We have two different kind of radicals here, and so we can simplify the square root of x terms into 4 square root of x, and then the square root of 3 comes out to be, or square root of 2 comes out to be 3 root 2. And in the case where you have different radicals, you examine them, see can you simplify them, and it looks like that square root of 27 can be simplified by taking the 27, factoring that to 3 cubed, and then we can take a 3 out of that radical, and so we get 24 root 3 minus 3 root 3, and of course then that makes 21 root 3. So here's one involving a variable y. Now we can take the square root of 25 and the square root of 64, and so we get 5 square root of y plus 8 square root of y, and we get 13 square root of y. Another example where we have 8 times the square root of x cubed plus x times square root of 81x. First we'll simplify both. We can take out an x squared, and then we can simplify this further by adding the 8x and the 9x, and we get 17x, and of course times the square root of x. Okay, any questions on these? These are pretty much all the kinds of things that you'll see. Okay, so why don't you get started on a few of these, and I'll be passing back your quizzes and some homework. So we have 5 square root of x. Okay, then the next one. Catherine, did you get the next one?
Yeah, we couldn't really simplify.
Okay.
But I broke it down to 2 root 3 plus 3 root 2.
Great. Like that, right? Okay, so that's simplified. Okay, how about the next one? Efren, did you get this next one? No? Julia, did you get that? Any volunteers? Paulo?
It didn't really simplify all the way, but it went to 5 root 6 minus 2 root 3.
Okay. Very good. How about the next one? Alexi, did you get the next one? Not quite yet? Okay. Anybody else?
3 root 5 minus root 10.
Okay. All right. And then the very last one. Yes, Catherine.
Well, do you want the answer?
Yes.
Okay. 7 root 3x.
7 root 3x. Okay, very good. Uh-oh, I got 13. How did that work? I'm probably wrong here. Because this turned out to be 4 times 2 is 8.
I forgot to multiply before by 2. So
Okay.
yeah.
All right, so it's...
Other than that mistake, I
all right, everybody get these? Any questions on them before we go on? Okay, so let's go through a few more examples. Here I have with the cube root, we got the cube root of 54y to the 5th plus 4 cube root 2y squared. And so, you know, the key to all these are going to be, you know, properly factoring and then taking out the powers that are in excess of the indices. And so it simplifies like this, where that first radical, you can see we can take out a 3 and we can take out a y. Now with this, okay, normally you would think, well, you know, you're kind of simple there because you can't directly add 3y to 4, right? But we can put them in parentheses, and then have it multiplied by the common radical there. And here we're in kind of a little gray area about simplifying, because if you recall from the early parts of the book, they were talking about simplifying as eliminating all parentheses. That when we're doing something like this, we're actually factoring out the cube root of 2y squared. And so really, both of them are simple in a sense. This first one here, the one without the parentheses, is simple from the standpoint that we have terms that don't directly add. The second one, we really added the terms and factored out this cube root. And so it's a little bit ambiguous here, but for the purposes of this section, we're going to simplify to have the common radical factored out. Okay? So here's another one where we have the fourth root of 48, or 4 times the fourth root of 48, minus the fourth root of 243. And so one of the things that you should be at least reasonably good at is factoring. And so some of you use that tree format, you know, where you break it up into a little tree and you make a diagram like this, where you can say 48, and you say, okay, that's 2, and then 24, and you break up 24 to 2 and 12, and you break up the 12 to 2 and 6, and then the 6 is 2 and 3. Some of you do it like that, and the advantage of doing it with the tree is that you don't always have to factor it by prime factors. You just have to get it down to prime factors. So if you do something like this where you recognize 48 is actually 4 times 12, then you continue factoring each one until we get the prime factors. And so you notice I did it twice here with essentially 2 different strategies, and you get 2 to the 4th times 3 in both cases. And the way I do it, though, the way I prefer it, because I think it's a little bit more compact, and is that you just start with the lowest prime number, which is 2, and you start dividing, and you keep on doing that until you don't get something that's divisible by 2 anymore, and then you divide by the next lowest prime number, which is 3, and you count up 5, 7, 11, 13, 17, you know, and so on. And you only have to go, and you'll get down to a low number fairly quickly. So like for 243, perhaps doesn't factor quite as readily. It's not even, but we can start dividing by 3 because we know it's divisible by 3. 2 plus 4 is 6 plus 3 is 9. So anytime that the digits add to 3, you can divide by 3. And so I just keep on dividing by 3 until I'm done. And so I have these 2 factored. And so I'll rewrite this as the way it factors, and then simplify the radicals, and then we can combine the radicals to make 5 times the 4th root of 3. So either way you do it, I don't mind if you use this tree method. I think that's probably a little bit more commonly taught in the high schools. I don't know, I've just always preferred this way myself because it's a little bit more compact, and I'm doing division with smaller numbers. Here I'm having to imagine, how does 243 break up? And you know, your best bet is to start with low prime numbers, and so you when you're doing it like this, you almost always come out to exactly the same kind of thing. Okay, any questions with that? Okay, then why don't you give these a shot. Now look, we have one that has a ratio in here, so look at that one fairly carefully. Okay, and from there, so is that what you got?
Yeah, keep it.
Yeah. Okay, everybody good with that? All right, so how about the second one? Anybody? Yes.
I'm not sure if it's right, but I got 3 cube root 2x.
Okay. Tell me how you simplified that first one.
I broke up the numerator and the denominator. So I had 3 times 2 times x in the numerator. And the denominator then 2 cubed times 3.
Okay.
And then plus 3 root 2x. Oh wait. So this is,
Okay. So that's a good start.
I missed it.
You missed the 4. Okay, let me make a comment before you split this up into that first term. If we recognize, if we first factor, okay, and the numerator is 2 times 3x, the denominator is 2 cubed times 3, we can cancel out the 2's and get and take out a cube root on the bottom. So let me show you how we did this. So if we say cube root of 2 times 3x, and then 2 cubed times 3, and I'm just considering this first radical. Think about this now, if we can cancel these out. Now, if we cancel this out, this 2 over 2 cubed, we're going to have to rationalize ultimately the 2 cubed on the bottom. So one of the ways that we can do this now is now's the time to split it. So we get the cube root of 2 cubed. Sorry. And so this becomes then the cube root of 2x over 2, or we can put that as a coefficient of 1/2. All right, then the second one stays put, and so we have 4 plus 1/2, and so 4 is 8 halves, and so 8 halves plus 1/2 is 9 halves. Okay, any question on that? Now, if you did ultimately cancel out the 2's and rationalize it, you'll come out to exactly the same thing. You'll come out to the same same number. Now, if you didn't treat this as 1/2, what you have is 9 times the cube root of, oops, I'm ahead of myself here. If we have the cube root of 2x over 2 plus 4 times the cube root of 2x. Since we have the cube root of 2x in the numerator for both of them, we can make a common denominator here and say all of this is over 2, and so we have, this would be multiplied by 2, and so we have 8 cube root of 2x, and so this comes out to then 9 cube root of 2x over 2, which is exactly the same thing as if we were to write the 9 halves in front. Okay, so either method is fine. It's really just a question of form more than how the answer changes. Okay, so here, when you have a radical in the denominator, you might want to rationalize that before you simplify. So in this case, what we do is we rationalize the second term by multiplying it by radical 3 over radical 3. And so we'll get then 4 radical 3 over 3. And so now we can take the, this is essentially 1 in front of here. 1 minus 4/3 is going to be negative 1/3. And so we can combine those two. If we have something like this where we have a 3x, the square root of 3x in the denominator, we want to simplify the first one and rationalize the second radical. And so you can see what I did here was I factored the 12x to 2 squared 3, and then rationalizing the second radical, I'm multiplying it by the square root of 3x over the square root of 3x. And so what I end up with is 2 times the square root of 3x, and on the second term I have x times square root of 3x over 3x, and now the x's can cancel, and so what I get is essentially 1/3, so I have 2 minus 1/3. Well, 2 is actually 6/3, so 6/3 minus 1/3 is 5/3, and so then we're done there. All right, everybody see what I did there with these? So here's really a compelling case for rationalizing, is that when you have the opportunity to take like terms or take like radicals, you make sure they all end up in the numerator, and then you can more readily combine the radicals. All right, so here's a few for you. We have a 2 root 5x in the numerator, and so now that we have the common radical, what we want to do is we want to make a common denominator here, and the common denominator is 5x. So we're going to multiply the second one by 5x over 5x. Okay, and now that we have a common denominator, we can add the 2 plus the 5x, and then we end up with that over 5x. Of course, times the square root of 5x. Now, one of the things about doing this is that you can have much more complicated radicands with these radicals and still do the same kind of thing. And you're going to see this in calculus quite a bit. For example, if you have something like this, where you have 4 times the square root of 2x minus 1 plus 8 times the square root of 2x minus 1. This is no different than anything that we've done. The radicand is the same, and the index to the radical is the same. So we can just directly add the 4 and the 8 and get a 12 square root of 2x minus 1. So think of these radicals as just entities that have to match. It doesn't matter how complicated they are. Yeah, sorry, do you have a question?
Like, why couldn't you just, like, add the 4 square root 2 on the square root 2 and the other 2?
Why can't I just add these?
Like,
I did. 4 plus 1/2 is 9/2. What did you expect it to look like?
I don't know. I just don't understand.
Yeah, you can make it a common denominator, so over 2, so you have 8 over 2 would be the common denominator, and you have 8 plus 1 is 9. So you would you'd write it a little differently, 9 radical 2 all over 2, but it's the same thing. Okay? Okay, so keep this in mind. This is going to be something that you're going to use a lot in calculus when you're taking derivatives and you're going to be adding up different radicals that come out of using the various rules of differentiation. That's going to be kind of common. All right, so we actually have quite a bit of time left. So what I'd like to do is start into multiplying radicals. And multiplying radicals works just like multiplying things with exponents. Okay, so here we have square root of 5 times the square root of 2. Since they have the same index on the radical, we can actually multiply the two radicands together and have the well, it comes from the exponentiation rules. And so what we're looking for is the radicals having the same index. And so when we have something like the square root of 2 times the square root of 50, this simplifies out to the square root of 2, and if you wanted to, you could simplify this to be 5 times the square root of 2, and then multiply the two square roots of 2 together, and you get 2 times 5, which is 10. Or you can do this, multiply the 2 times 50, get the square root of 100, and of course that's 10. The distributive property works exactly the same as you would expect, where you have 3 times 2 plus the square root of 3, so that distributes just like you would expect. 3 times 2 is 6, 3 times the square root of 3 is 3 times the square root of 3. And when you have something like the square root on the outside of the parentheses, it comes out to be 5 times the square root of 3, and then the square root of 3 times the square root of 3 is the square root of 9, which is 3. Or you can just look at it as the square root of 3 times the square root of 3 equals 3. Okay? Now, if you have something like this, where you have the square root of 2 times the square root of, or the cube root of 3, this is already simplified. There's nothing you can do here with this, because the index is different and the base is different, or the radicand is different. So if you, so we have two different rules here. We have, or sets of rules. We talked about multiplication where the radicands are the same. We can do that, and we can now do it when the indexes are the same. But when they're mixed, when the radicand and the index are different, then you can't do anything. So to give you an example, earlier we did something like this. If you take the cube root of 5x times, let's say, the 4th root of 5x. Okay, so with this one, what we want to do is we want to put it in exponential form. And so we have 5x to the 1/3 times 5x to the 1/4. And since we have the same base now here, we can add the exponents. So we can say, okay, this is going to be 5x to the 1/3 plus 1/4. And so the common denominator there is 12. And so this is going to be 4/12 plus 3/12. So this will be 5x to the 7/12. Okay, so notice the difference here. Now if I take something like the cube root of 5x times the cube root of, let's say, 13, the index is the same, all right? So what we do is we just multiply the radicands, and so we have 13 times 5 is going to be 65x, and that's all to the 3rd root. Now if we have, like I wrote at the bottom of that, if I combine these two, let's say the cube root of 5x times the 4th root of 13, there's nothing to do here. There's nothing you can do. It doesn't work to multiply the radicands. It doesn't work to add the indices. So even if we wrote this in exponential form, see, there's nothing we can do with this. So here, the radicands are the same. Here, the indexes are the same. So there is something you can do to both of these. When both of them are different, there's nothing you can do. And so that's hopefully not too confusing. You just have to remember what's the basis of this. The basis of this is adding exponents. The basis of this is that you have the same index. And so you're using this rule here where you have, a to the n times b to the n equals ab to the n.